The automated threat evaluation of various RISC-V alternatives using random instruction generator. Abstract. Safety-critical designs require fast, automated, and low overhead verification techniques to cope with the ever-increasing complexity and shortening time to market constraint. Consequently, engineers are constantly looking for the highly efficient verification approaches. In this paper, we propose an automated safety verification technique that combines model-driven fault simulation and model-driven random instruction generation. The technique performs exhaustive fault injection and statistically fault injection with minimal effort, and at the same time provides acceptable fault coverage faults when low performance overhead. The proposed approach scales a wide variety of RISC-V CPU subsystems and experimental results achieve the fault coverage rate of the 40% up to 99% while conducting the fault injection on different components of the CPU. Chapter 1. Instruction and Background. The complexity of the size of the system stems on chips are constantly increasing, and consequently they are facing a higher risk of failure. Radiation, aging, mechanical stress, and a processing defect could lead to undesired failure event. Safety-critical designs need to guarantee a continuous, reliable, and safe operations even under harsh operating conditions. Thus, various fault decision and corrections mechanisms are required to mitigate the defect of the hardware faults. The automotive industry has adopted ISO 26262 to standard data implementation, verification, and validation of the safety-critical designs. Fault injection is recommended technique to evaluate the risk dependability and the designs, and it is defined as observation of the behavior of the system in the presence of the intentionally injected fault. So the state-of-the-art fault injection techniques are divided into the following categories: hardware-based and software-based, and simulation-based and emulation-based, and hardware hybrid-based. Improvement in the fault injection processes is required to fulfill the ever shortening the time to market deadline in the industry. So therefore, it's required to have a higher degree of automation to increase the productivity. Eckhart et al. In reference 3 and reference 4 presented the automated RTL generation framework, namely Meta-RTL. Meta-RTL is a proprietary framework that describes a component of RTL, for example, logic gate, registers, and etc., and utilizes the built-in Python APIs to generate the RTL from the top-level meta-model specification. In addition, Meta-RTL utilizes a library of the components, which are classical building blocks for generated designs. The framework reduces significantly the manual effort and at the same time increases design productivity. In this paper, an automated simulated dependent mixed granularity fault injector, scale level, register, and register transfer level is utilized to injection different types of the fault hardware ports. The fault injection framework utilizes the above-mentioned RTL generation framework. Figure 1 presents the generation flow of the design with a fault injection capability using saboteur-based techniques. The selected parts of the design are subject to a fault injection are kept on gate level granularity, while the rest of the design is represented on the traditional register transfer level RTL granularity. To achieve that, the script TOD generator, figure 1, is released data from the level analyst and technology library and generate a new template of the design TOD of mixed RTL and GL granularity level. So the TOD is a microarchitecture blueprint of the intended design. As the next step, saboteurs are added to the model of design, which is a platform and technology independent hardware description. Saboteur control lines are propagated as primary input and the existing RTL generation flow is used to generate the design and mixed granularity flavor. So in the end, the formal equivalent check is applied to check whether the transformation process has introduced any bug in the new design. The presented flow enables for fast RTL simulation without losing the accuracy of the gate-level fault simulation. So although the fault simulation is advantageous in several aspects, an automated approach covering all aspects of the fault simulation is required to keep the annual effort low. So the safety critical designs demand rigorous, stringent and automated verification techniques with minimal effort. Moreover, the complex test techniques are required to achieve the acceptable fault coverage according to the different standards. Fault coverage is defined as the ratio of the detectable fault to the total faults, and various approaches have been developed to increase the overall coverage. Nevertheless, the widely used techniques, for example built-in self-test, suffer from the performance and area constraint. To combat the existing drawback, we present in this paper and the approaches to combine model-driven and hardware generation and model-driven fast simulation to automatically evaluate RISC-V designed fault coverage with minimal manual effort. Section 2, Chapter 2 is related work. The fault injection and safety verification is a well-researched topic in academia as well as industry. In the following, some of the related techniques are presented. Cadence Jasper FSV enables a formal fault injection and propagation analysis to support the safety and security verification. So similarly, fault injection application and fault propagation analysis from the one spin provide from the verification method to verify the safety mechanisms. The interface enables the user to decline the custom fault scenarios or pick the predefined ones. It's necessary to mention the previously described tools are vendor specific. Gen5 is an approach from the academia to inject faults on the microarchitecture simulator such as MARS, MARSS, and Gen5, GEM5, and while Baraja et al. So reference 10 and 11 modify the hardware description and the design utilizing the saboteur and a mutant. In reference 12, authors propose authors propose a Verilog-based framework to perform fault injection based on a Verilog programming interface, VPI. So chapter 3, RISC-V CPU generation. The in-house model-driven RTL generation framework, MetaRTL, enables productivity increase thanks to the flexibility of the Python-based APIs. The approaches provide freedom for various R-target HDL and at the same time generate various design alternatives while utilizing the same Python code. The key element of the generation framework in the meta model. A meta model represents a structure of a model, its attribute and the relation between them. That is, it formalizes the informal specification to well-structured formal specification. So field 2 is presented the RISC meta model as a unified markup language UML class diagram. This meta model is used to generate various RISC-V alternative 13 depending on model configuration. The figure 2 is the RISC-V meta model. So four main components compose the meta RISC: encoding tree, instruction, architecture state, and exceptions. Encoding tree builds a tree-like structure to determine the parameters and the format of all instructions. The high degree of flexibility facilitates supporting different types of instruction sets. Instructions describe the instruction and its behavior. That is, the changes the instruction prompt in the architectural state of the CPU. Architectural state is present in the important state element of the CPU, such as a program counter, PC, and general purpose register, GPR, and control and status register, CSR. The exceptions are the set of the exceptions, unexpected events, and their behavior. The user needs to fill the model with the desired configuration, and using meta-RTL and various RISC-V alternatives can be generated. Chapter 4 is model-based fault simulation framework. The flexibility of the generation framework will facilitate the development of the automated and configurable model-driven fault simulation framework. The framework stands to build up to the fault injection flow presented in Section 1. The fault simulation framework BetaFS is presented in Figure 3a. BetaFS is composed of the three main components: simulation control, and fault list, and fault analyzer. The simulation controller allows the user to define more total simulation time and enable timing fault and choose different fault injection campaigns such as statistical fault injection (SFI), exhaustive fault injection (EFI), and directed fault injection (DFI). So during the SFI campaign, only a certain random subset of all possible errors is injected. The design safety dependability is measured with a certain degree of confidence. SFI class permits the user to determine the number of faults in the injection per simulation and the total amount of the simulation. Further, Boolean attribute of this class activate the SEU single event offset and timing fault. All faults are injected randomly combined with the user configuration. During the EFI campaign, the all struct error faults are injected into all design signals. The user is able to choose injection and release time using EFI class. Attribute of the DFI class determine the injection predefined fault models is predefined signals during certain clock cycles. The Figure 3 is automated test bench generation, fault simulation meta model, and generated test bench. A Python script to collect the data from the design and provide the necessary information to fill the attribute of the fault list class. The scalar class defines the design signals and respective saboteur control line to injection fault. Fault model define all possible fault models to inject due to the fact the fault collapse, eliminating the redundant fault. Simulation analyzer provides the necessary information to analyze and classify the injected fault. The user fills the method model attribute with the desired signals, internal signal registers, as well as with the primary output to analyze via strobe class. Additionally, it is possible to specify whether the selected signal is a functional output or an output of the safety mechanism. The framework generated system value and CW plus test bench in accordance with the meta model data. Figure 3b represents a snippet of a generated fault simulation test bench. Line 3 and 19 and 30 represented the simulation count, and in this case, the user has selected to inject only 3 faults, line 4 and 20. The 3 faults. Line 4, lines 4 and 12 and 31 define the time point when the fault should be injected at line 10, and 26 and 37 determine the fault model to inject. That is, random saboteur control lines are driven to inject a particular fault model. During simulation, 1 and 3 and bit flop is injected since the fault is kept high only for 1 o'clock, and during the simulation 2 and fault is kept high for the whole duration of the simulation. The last of lines of stores the simulation data is low-fi. Figure 4 describes the completed fault simulation flow on a block level. After generating duty utilizing the meta-RTL and the fault simulation framework generate necessary test benches to perform fault simulation campaign. After storing the data in the log file at each faulty simulation, the test bench compares this data to the golden known faulty simulation This compiler classified the faults according to their effect on the design behavior. As a last step, the fault classification's results are stored in a log file. A snippet of this file is shown in Figure 5, and each column represents the following data: the fault theme, fault simulation count, fault injection time, fault inject time, the fault injection time, fault propagate time. It shows the timeout when the fault has propagated to any of the strobe selected by the user. If fault did not propagate, the symbol NA will be displayed. Propagated F strobe display the strobe signals where the fault propagated. Fault detect time displays the time out when the fault was detected by a safety mechanism. If not, NA will be displayed. Detected C strobe display which checker strobe was detected in that injected fault. Figure 5 fault simulation result. At the end of the file, the collection of this data will be shown. Safety undetected faults, a fault that did not propagate at any strobe. Safety detected fault, fault that are detected and fixed by the safety mechanism. Dangerous undetected fault, fault that are propagated to the functional strobe are not detected by the safety mechanism. Dangerous undetected fault, fault that are propagated to the functional strobe but not detected by safety mechanism. It's necessary to note that this approach is design dependent. That is, fault injection can be applied to all kinds of design generated by meta-RTL, prefer and safety mechanism, and etc. Chapter 5 Random Instruction Generation. Safety critical designs require rigorous verification and testing to comply with different international standards. Automatic test to pattern generation (ATPG) and built-in self-test (BIST) and the most common techniques that provide adequate input to test sequences for the dependability evaluation of safety critical designs. Even though the techniques provide a very high fault coverage result, they suffer from the area and perform constraint. ISO 26262, the international standard for automotive safety, and recommends various automotive safety integrity levels (ASILs) for different designs. Consequently, a low overhead random input test sequence can be utilized to achieve the acceptable fault coverage result. So the model-driven fault simulation framework is combined to the model-driven random RISC-V instruction generation as input to stimuli to automatically evaluate fault coverage of various RISC-V-based CPU subsystems. So the key element of a random instruction generator is a meta model presented in Figure 2a. A Python script reads the model data and generates the instruction accordingly. That is, to generate a value of an instruction as defined in the model from section 3. The generated script is highly configurable, and thus the user can constrain the test. In the following, the configurable parameters are shown. Constraint. The user can constrain the class of instruction to generate, that is, only load and CSR type instructions. Further, if it is possible to constrain instruction to have read after write dependencies. Length. The user can specify the number of instructions to be generated. The varying the length of the test sequence is an important factor that impacts the fault coverage result. File type. Support two different file types such as hex and binary. As memory start address, the user can specify as an integer the starting address of the data memory. After configuring the generator, the framework APIs are utilized to read model data and generate a set of the random instruction, which serves as test input for the RISC-V CPU. Chapter 6 Application and Result. The applicability and the low cost of combining random instruction generation with the fault simulation flow have been in demonstration on CPU subsystem with various RISC-V CPU alternatives. The subsystem is composed of the CPU and program and data memory instances, peripherals such as SPI, UART, interrupt controller, and a bus fabric with bus bridges. The test on 3 similar subsystems with different RISC-V alternatives, that is, only a CPU changes, the input set since section 5 is loaded into instruction memory and various lengths of the test sequence have been applied. The following subsections present the fault coverage ledger of the CPU while applying random instruction as test stimuli on 3 RISC-V CPU subsystems, respectively RV32IMC, RV32IMC exceptions, and RV32IMC -MAC. The edge test input length of 100, 150, 200, 250, and 300 instruction was utilized. Faults were injected only one particular component of the CPU, such as the arithmetic logic unit ALU, the forwarding unit FW unit, and prepatcher and fetch stage. And figure 6 to 8 display the fault coverage ledger of the EFI campaign, and the total amount of injected fault is shown in the right side of the figure. Figure 9 presented the SFI campaign ledger, as all the campaigns were run on the Xcelium simulator. A RB32IMC EFI campaign, as shown in figure 6, fault coverage increased constantly with the higher set of the input of all component faults except for the IALU faults. For the forwarding unit fault goes up to the 99% fault coverage rate for an input set of the 300 random instructions. The steepest incline of the fault coverage was observed while the injection fault of prepatcher, but it is stabilized after 250 instructions. Interestingly, the input stimuli do not sensitize to many fetch stage fault, and one region for that the random jumps and branches to out of memory locations. Figure 6 RV32IMC EFI campaign. Section B, RV32IMC exception EFI campaign. An exception unit EU is added to CPU during this campaign to support exception handling. Similar ledger to the RV32IMC EFI campaign were observed as presented figure 7. A slight increase of the fault coverage was noticed all components except for the forward unit, where it remained the same. Further, the total amount of injected fault of the fetch stage is higher due to the added EU. Section C is RV32IMC and IMAC, the EFI campaign. The EFI campaign is applied to the CPU with support for exception and the MAC extension. In figure 8, there are noticed almost identical ledger to RV32IMC exceptions EFI campaign. See figure 7 with a slight increase of fault coverage to the ALU faults. D. SFI campaign. During the SFI campaign, there were injected random fault models, including stockhead, SCU, and timing faults on random fault locations during random time points. The test length was 300 instructions, and figure 9 represents the fault simulation ledger on all components like in the previous campaigns. Fault coverage has significantly reduced compared to EFI campaign. Thus, SEU and timing faults have had a low impact on the selected component. Figure 7 RV32 IMC exceptions EFI campaigns. Figure 8 RV32 IMC MAC EFI campaign. Figure 9 SFI campaign of 3 CPU variants. The chapter 7, Conclusion and Future Work. In this paper, we introduced a low overhead automated safety evaluation of various RISC-V alternatives by combining model-driven force simulation and model-driven random instruction generation. The framework is generic, and a fault injection can be applied to various distinct designs. Numerous experiments were conducted on 3 different RISC-V CPU subsystems with varying length of the test sequences. The exhaustive fault injection campaign resulted in an acceptable fault coverage range 40% to 99% for the length of the input test of 300 instructions. That is, with a minimal memory footprint, the total effort required to run all the campaign was 1 person day. Expanding the support fault models, constraining jumps to the inbound memory location, and further comparison to other commercial and open source fault simulation tools is subjected to future work. Due to internal policy, the framework is not intended to be provided as open source in the near future. Chapter 8, Acknowledgement. The references. Okay, today I read this paper, Automated Thread Evaluation of Various RISC-V Alternatives Using Random Instruction Generator from DVCON2023 conference. Thank you for your time. See you next time.